now let us discuss about what is velocity saturation. So this is my MOSFET here. For N MOSFET, the source and bulb has to be grounded. Okay, and for drain you have to give a positive voltage. Okay, so this will attract my electron to flow in this direction, right? So the electron will flow in this direction so that my IDS will flow in this direction, right? So what will happen, so if I increase the value of VDS, my electron will attain the larger drift velocity. Okay, so I can write, if I apply the electric field E, so E is equal to VDS by this length of the MOSFET. Okay, so what will happen if I shrink this length? So if I bring this drain, if I shrink this length of the MOSFET, okay, so it will attain the saturation even before the previous one, right? So if you know, if I plot the graph between the velocity and the electric field, so we know that the velocity, okay, velocity is equal to, that is drift velocity, okay, drift velocity, Vd is equal to mu into E. Vd is equal to mu into E. So, so it is linear with respect to mu, and it will attain some maximum value, right? That is called Vd saturation. So the Vd saturation value is nothing but 10 power 5 meter per second. So I can write Vd saturation is equal to mu n. Here it is n, n MOS, so I can write it as mu n into E saturation, right? So here I can write it as E saturation. Okay, so since I have reduced this equation, I can write E saturation, okay, is equal to Vd S saturation divided by L. So this is for short channel. So I can substitute this in this is my first equation. This is my first equation and this is my second equation. So I'm going to substitute 2 in 1. If I substitute 2 in 1, I can write this velocity, drift velocity saturation is equal to mu n VDS sat divided by L. So VDS saturation is equal to L into Vd sat divided by n. See, if this equation is not present in anywhere in these 3 equations. So IDS is equal to 0 when VGS is less than VT. That is for cutoff region. And we know that IDS value is equal to mu n Cox W by L VGS minus VT into VDS minus VDS square divided by 2 when VDS is less than VGS minus VT. Okay, so this is for linear region, right? This is for linear region. And for saturation region, so you have to substitute mu n Cox W by L. Instead of VDS, you have to substitute VDS. Okay, VDS is greater than or equal to VGS minus VT, right? So I can substitute if I substitute instead of VDS, if I substitute VGS minus VT, I will get VGS minus VT whole square divided by 2. So this is for saturation region. So if I plot the graph between the VGS, IDS and the VDS, so you can see this is a plot for IDS and VDS. Okay, so for smaller value of VGS, consider this is my VGS value is equal to 0.4 volt. Okay, so for smaller value of VGS, it will attain and we consider another value. Okay, so VGS is equal to 0.6 volt. So here it is attaining a saturation value. So that value is nothing but VGS minus VT. Okay, so here you can see the EC is a value where it is attaining the saturation value. Further, it will not the velocity will not increase. So that is called as saturation. Okay, so since I am shrinking the length of the MOSFET, so it will attain the saturation even before this value. So I can write that value is nothing but so this is attaining the saturation value at this point. Okay, so I can write this one as VDS saturation. That is even before the VDS minus VGS minus VT. So my the IDS value will look like this. Okay, for VGS is equal to 0.6 volt. Okay, so you can see due to this the current value get decreased. Okay, so this is called as velocity saturation. So I can write this equation. Okay, in so I can write this as unified current model. That is IDS is equal to beta. This I can write it as beta n into this whole thing VGS minus VT Vmin minus Vmin square divided by 2, where my Vmin is equal to minimum value of VGS minus VT, or it may be VD sat, or it may be VDS. Okay, so if I substitute VGS minus VT means it is nothing but a saturation. Okay, saturation value, and VDS sat means it is velocity saturation. And if I substitute VDS means it is in the linear region. So here due to the lateral electric field, what is lateral electric field means the electric field is in the horizontal direction. Okay, so due to the high lateral field. Okay, so what is the definition is high lateral field strength the carrier velocity. Okay, carrier velocity C ceases means stop to increases. Okay, stop to increase linearly with field strength. So this is called as velocity saturation, which will result in the lower IDS than it is expected at the high VDs. Okay. So this so you can see due to the velocity saturation. What is the velocity saturation means? If you are in a if you are in a courtyard, if the wind is blowing, means you are trying to go fast, right? So often you will get collided, and beyond a certain level, you will get fatigue, and you will reach some maximum average speed, right? So like in the same way, this carrier will approach as a maximum velocity, that is called as V saturation, velocity saturation, when the high field is applied. So this phenomenon is called as velocity saturation. So EC means it is critical. C represents critical. You have to apply very less supply voltage, right? Since it is we are shrinking the length of the MOSFET, we have to apply a less supply voltage compared to the long channel effect. So let us discuss another non-ideal effects of MOSFET, that is channel length modulation. CLM, okay. So here if you see this is my gate and the source and drain. Okay, so if I increase the VDS further, okay, so here I am giving the reverse bias, okay, reverse bias to the drain. Okay, so I am giving a positive value to drain and negative value to the source. So if I give a reverse bias to this P and N type, the depletion region get increased. So if the depletion region increase, my channel length start to decrease, right? So and this point is called as pinch off region, right? So originally my channel length is L, okay, my channel length is L. Since I have increased the value of VDS, the channel length get reduced to L bar, okay. So I can write L is equal to L plus L dash plus del L, okay. So this is the VA configuration, okay. So if I increase the VDS further, okay, what will happen, instead of this blue line, I am going to get this pink line, okay. So this is due to the channel length modulation. So on the difference I can write it as del V, okay. So from this equation I can write L bar is L dash is equal to L minus del L, okay. I can write del L divided by L as proportionate to VDS, because the change in the length of the channel is with respect to L is due to the change in the VDS. So I can write del L divided by L is equal to lambda VDS. So here if I take the L common, I will get L into 1 minus del L divided by L. So you substitute this value, okay. So if you substitute this value, I will get L bar is equal to L into 1 minus lambda VDS, okay. So we know that the IDS equation is equal to beta VGS minus VT the whole square divided by 2, right? Where beta is equal to mu n Cox W by L. Okay, so here I have to write mu n Cox W by L bar. Okay, VGS minus VT the whole square divided by 2. Okay, so instead of L bar, I'm going to substitute this first equation. So if I substitute the first equation, I will get ID is equal to mu n Cox W divided by L into 1 minus lambda VDS the whole power minus 1. VGS minus VT the whole square divided by 2. Okay. So I can write 1 minus lambda VDS minus 1 is equal to 1 plus lambda VDS. Okay. So I substitute this value. Instead of this one, you substitute this. Okay. So you can see this whole term. Now this whole term will look like ID. Okay. So I can write ID with channel length modulation is equal to ID without channel length modulation into 1 plus lambda VDS.